All right. Hello, and welcome to the ASCM Grand Rapids Professional Development Meeting. I'm Kathy Bosher. I'm the treasurer of this chapter, and I'm excited to introduce our presenter, Dr. Louisa Rebel. Dr. Rebel is a research astronomer at the NASA IPAC Infrared Science Archive, URSA, at Caltech IPAC. She got her undergraduate degree in physics from the College of William and Mary in Virginia, and her graduate degree in astronomy and astrophysics from the University of Chicago. She has been on the science staff of IPAC since 2002. Her research focuses on the formation of young, low-mass stars all over the galaxy and understanding how stellar rotation changes over the first billion years of a star's life. In addition to her professional accomplishments, Louisa has also been married to my brother, Dave Cole, for 21 years. Dave's also an astronomer and a graduate of Calvin University. And she is also the mother to my 13-year-old nephew, Andrew. So welcome, Louisa.
Thanks very much. Thanks very much for inviting me. And since we are a small enough group, I am totally good with, if you have questions, just unmute and ask them because we're not that big of a group. I have also learned at this point in the pandemic that I can watch the time and the slides and remember what I want to say, but I cannot also watch the chat. So if you guys have questions, you can either just unmute and
maybe want to
ask. Although I can hear somebody trying to ask something or maybe just inadvertently unmuted. And then if you don't feel comfortable doing that, you can put them in the chat. And then Kathy, if you want to watch the chat and just ask any questions that people have, that would be great. Let's see, why is it not going forward? Come on, there we go. So there we go. So so I'll first start at the beginning with what is infrared light, and I'll talk a little bit about Spitzer itself. Spitzer, the telescope that's going to be the heart of what I'm going to talk about, but also put it in context with some other spacecraft, including James Webb, the telescope that just launched a couple of weeks ago. And I'll give you some highlights of Spitzer's science results, which I'm going to admit straight off the bat is highly incomplete because I only have you for an hour, and I'm going to give you a highly biased and incomplete summary of Spitzer's accomplishments because I do study things in our galaxy. I'm going to focus on those kinds of science results. And then the last couple of slides I have are all about how this is your data too, and talk about how you can access data too. So NASA has several different space telescopes, but there are only 4 that have the special title Great Observatory. So and they span all kinds of electromagnetic radiation, all kinds of light. So there was the Compton Gamma Ray Observatory, which observed in gamma rays. There's the Chandra X-ray Observatory, which observes in X-rays. There's the Hubble Space Telescope, which observes in optical or visible light. And there was the Spitzer Infrared Telescope, which observes in the infrared. The new telescope is called the James Webb Space Telescope, JWST. It is not technically a great observatory, but it is still a flagship mission. And both of those words mean something to NASA budget wonks. It has to do with exactly where the funding is coming from. But James Webb observes in both optical and near infrared. So what does that mean? When, in astronomy, we're studying things that we can never, ever visit. We can't even turn them around and see them from another angle. So we have to take advantage of all of the information that we're getting from these objects. And so we have to observe them in as many different wavelengths of light as we can. So this is the same galaxy seen at many different wavelengths. On the left, that's an X-ray image taken by the Chandra X-ray Observatory. This is an ultraviolet or UV image taken with a spacecraft called GALAX. This is an optical or visible light taken from the Hubble Space Telescope. This is a near infrared image, which the data here are taken from 2MASS, which is a ground-based near infrared survey, but it also has Spitzer data, which is from the Spitzer Space Telescope. And then the last image here is in the far infrared, which is a combination of Spitzer and Herschel Space Telescope data. So the light that you're seeing here is very different. And if you look across the same galaxy, different details are apparent. The galaxy looks very, very different across all of these different wavelengths. So in the X-rays, the kind of light that you're looking at, the wavelength of light is 2 nanometers. A nanometer is a billionth of a meter. And so the light, the temperature of the things that you're looking at are very hot, like 1,000,000 Kelvin. And so the kinds of things you're looking at include things like black hole accretion disks. In the ultraviolet, you're looking at wavelengths of light that are maybe 200 nanometers or temperatures of like 15,000 Kelvin. And those tend to be hot stars, which are also the young stars. In visible light, you're looking at wavelengths of light that are 500 nanometers or half a micron. A micron is a millionth of a meter. So you're looking at things that are maybe 6,000 Kelvin, and those tend to be run-of-the-mill stars. So average stars like our sun, all ages. In the near infrared, you're looking at wavelengths of light that are like 1,600 nanometers or 1.6 microns. You're looking at things that are 2,000 Kelvin. Those tend to be very cool stars, which are usually the old stars. In the far infrared, you're looking at wavelengths of light that are like 100,000 nanometers or 100 microns. Things are like 30 Kelvin, so very much colder than anything else we've been looking at. That tends to be the cool dust, which is heated by the hot stars. So look, there are things that are bright in X-rays that are not at all bright at the other wavelengths. Things that are bright in the far infrared that are not at all bright in the other wavelengths. Things that are dark in the visible that are bright in the infrared. So you're learning very different things when you look at the same galaxy in many different wavelengths. So where does James Webb fit in? Right in between those two. It observes in some longer wavelength lights, longer wavelength visible light, and some shorter wavelength infrared light. So I work at IPAC, and we have a very biased view of the electromagnetic spectrum. We tend to do a lot of infrared astronomy at IPAC. We do a lot of infrared. We do at URSA, we're the infrared, we're the home for all of NASA's long wavelength data. So we do a lot of infrared at IPAC. So I'm going to focus on the infrared. So here's the same little dog seen in visible light on the left and in infrared light on the right. So there's two very important things to note right away. One is that this is something I'm calling a remapped color image. Now, sometimes in astronomy, you hear the term false color. False color implies that I'm hiding something, I'm doing something fake. But a true color infrared image is really rather boring because your eyes can't see infrared light. So instead, I'm taking those infrared photons, and I'm remapping them into colors you can see. Hence, remapped color is a better choice of words rather than false color. And the other important thing to know is that the way that I'm choosing to do that is I'm mapping those infrared photons to colors you can see in colors corresponding to a temperature scale. So things that are white or yellow are much warmer than things that are black or purple. So in this case, his water dish is cold. His face is really fluffy. So you've got this halo of fur that's cool. His ears are warm. His face is warm. His eyes are very warm, but he's a healthy little dog, so his nose is cold. So now you know that hot things glow in the infrared. So which one is the hot water? It's the one on the bottom.
Yeah.
You can see the base of the faucet is heating up when the hot water is on. But when the hot water is on, the base of the cold water faucet is still cold. The basin is heating up when the hot water is on. You can tell what temperature it is by looking in the infrared. So now you know that infrared can reveal things hidden in visible light. What do you think that's going to look like? Think for a minute. I can tell you the hairdryer is on. You can see the hot air, even the turbulence in the hot air. You can see the heating elements in the hairdryer. Infrared can see through some things that are totally opaque in visible light. This is just a regular garden garbage bag, and you can see straight through it in the infrared. And it turns out that you personally are really, really grateful that infrared can see through some things that are totally opaque in visible light. Because if you are ever unconscious in a burning building filled with smoke, this is how the firefighters will find you. It is absolutely standard equipment in most firehouses to have an infrared camera, often a handheld infrared camera, for exactly this reason. Once you know the firefighter is there, you can pick him or her out through the smoke on the left. But if you didn't know that the firefighter was there, you would be hard pressed to find them in the smoke. So finding an unconscious body in the smoke is really very much easier if you've got an infrared camera. And with the infrared camera, you can find the firefighter in their firefighting gear, and you can see that this firefighter has something that's going to keep the firefighter cool when they're fighting the fire, because you can see that the backpack there is probably providing not only oxygen, but cooling mechanism underneath all of his hot clothing. You can see that there's heat escaping under all of the gear there. So some things that are transparent and visible light are completely opaque in the infrared. So this is a set of French doors, glass doors in my living room. One is closed and one is open. You can see straight through the glass in the optical, but you cannot see through the glass in the infrared at all. This is why in the summer, when you park your car in the sun, when you first get in, you have to drive the steering wheel like this. So the next time you cannot touch your steering wheel, think of all the infrared that's trapped in your car. The optical light from the sun comes through the windows of your car, heats up the inside of your car, and then the infrared can't get out. So the infrared is trapped. And that's why it hurts to sit on your car seat in the sun, and why you can't touch your steering wheel, because of all the infrared that's trapped in your car. So up until this point, I've been showing you infrared pictures of sort of everyday things. Now we're going to leave the everyday. Here, I've got something astronomers call a dewar. It's really just a fancy name for a thermos bottle. And I've got liquid nitrogen in it here. And I'm going to put frozen peas in it. But here on the upper left, I don't have any frozen peas in it yet. It's just liquid nitrogen. And the liquid nitrogen is at like 70 Kelvin, which is much colder than the camera can see. So the camera just gives up and covers and colors the whole inside of the dewar black, because it doesn't know what else to do, right? But now I'm going to put frozen peas inside the liquid nitrogen. And even though the frozen peas are cold, they're warm compared to the background, so the camera can see them. And that's exactly what's going on in space. Even though when we use the infrared in astronomy, we're seeing very cold things, but they're warm compared to the background. So they glow in the infrared. So this is the familiar constellation Orion in the optical. And here it is in the infrared. How much you miss if you limit yourself to just the optical. There's so much going on in Orion. You might know that the sword of Orion is a star forming region, but it turns out to be a massive star forming nursery, a massive complex of star formation with millions of baby stars in it. It turns out that the belt is a slightly older star forming region that is also generating stars. And here you can see a big circle of nebulosity, a big circle of fluffy stuff around Orion's head. Anytime you see a circle like that, it's a dead giveaway in astronomy that something has blown up. So almost certainly it was a massive star that has either blown that hole just by being a massive star, or actually having popped off as a supernova. So, and then you probably didn't even know there was a big star forming region over here too. You can barely see any evidence of it in the optical, but it's really obvious in the infrared. So why do we need to go to space to do infrared astronomy? Well, there's two big reasons. One is that space is cold. If you're looking for tiny little bits of heat, your telescope better be cold. If you're trying to do astronomy, infrared astronomy from the ground, your telescope is the same temperature as the air around you. And so the best analogy that I've heard is when you're doing infrared astronomy from the ground, it's like trying to do optical astronomy from a telescope made out of those long fluorescent tubes, because your telescope itself is glowing in the infrared. So it's really hard to do astronomy, infrared astronomy from the ground, because the telescope itself is glowing in the infrared. The other big reason is that the atmosphere itself absorbs infrared light. So here I've got a cartoon that's got transmission. In other words, how easily does the light make it through the atmosphere, roughly as a function of wavelength. So if you are a gamma ray astronomer, an X-ray astronomer, an ultraviolet astronomer, you have no hope. You have got to go to space. You have no choice, because those wavelengths don't really make it down to the ground unscathed. Optical light obviously makes it down to the ground. Now, infrared light. sometimes makes it down to the ground. If you pick your wavelength exactly right, you go to a very high, very dry location like Mauna Kea in Hawaii or Mount Palomar here in Southern California, and you have a very dry night, you have a pretty good chance of observing at some wavelengths. But for the longer infrared wavelengths, again, you have no hope. You've got to go to space. And the radio, again, makes it down to the ground. So this is what Spitzer's launch looked like. It was launched from Cape Canaveral in August 2003, and this is really, really, really what it looked like. If you've never been down to Cape Canaveral, all of the pictures you've seen of people watching launches, all of the stands, the grandstands for people watching launches, those are optimized for crewed mission launches. The uncrewed launches are actually from completely different launch pads, and all of those grandstands are not in a good place for watching the things that launch space robots. So for the launch pad that Spitzer was going from, the best place to launch it was actually a fishing pier in a park that's just south of the Cape. So this was the middle of the night in August. And so this is really, really what it looked like. So there's several hundred astronomers on a fishing pier with about a dozen really annoyed fishermen in the middle of the night. So this is really what it looked like when Spitzer launched. So this was about 18 years ago, but yeah, it launched and it did great. So the telescope was named for Spitzer Lyman Spitzer. This name was chosen from more than 7,000 entries submitted by the public to NASA. The Lyman Spitzer did a lot of interesting things, but the thing that I always remember was that in 1946, Spitzer was the first to propose putting a telescope into space. Think about that. In 1946, the only rockets that we really had as a human race were German V2s. And he had the vision to say, okay, let's not make warheads out of these. Let's put a telescope on a rocket, get it up above the atmosphere and see what we can see. He was a primary force behind funding Hubble, the space telescope. So this was that's a big deal, right? And so that's part of why they named the telescope after Lyman Spitzer. The other big reason is that Spitzer studied the interstellar medium, the fluffy stuff between the stars, the stuff, the dust, or the gas that stars are made out of. And you'll see that that is what Spitzer the telescope studied a lot of. So this is Spitzer the spacecraft. It was originally designed to be a fairly big thing in which the telescope itself, this little red thing, was entirely subsumed within cryogen, in other words, liquid helium, so really, really cold stuff. And so the entire telescope was subsumed in a bath of liquid helium inside of this big structure. And so when it was originally designed, that was the state of the art at the time. But there were lots and lots of budget cuts at NASA in the 90s, and it was nearly cut from the budget several times. But lots of really clever engineers figured out how to make this much smaller and therefore much cheaper to build and test and launch. So the telescope is the same size between these two designs, but the telescope itself is, or the spacecraft itself is much smaller. So it's much cheaper to launch. And the amount of cryogen you have to keep on board is much smaller as well. You can see with these people, it's not a big spacecraft. It's really rather small. The telescope itself lives in here. This is where the cryogen is. The instruments are in here. You can see the solar panels are here. And the solar panels shield the rest of the spacecraft from the sun. The side of this part is painted silver so that any little bits of sunlight that make it past the solar panels get reflected. The far side is painted black so that it can passively radiate any little bit of heat that gets through away into space. The thermodynamics of Spitzer, how you keep the telescope cold, is fascinating and is a whole talk unto itself, because the instruments down here, all of the electronics, they're generating heat, but you got to keep the telescope and the instruments cold. So the thermodynamics of how you do that, how you keep the instruments cold while still communicating to the electronics, which have to be warm, that's a tough problem, but they managed it. So all you see these struts here, that's the only way it's connected. The telescope is connected to what the engineers call the spacecraft, which is all the electronics and things down here. So there are very few moving parts in this spacecraft. So again, I want to try to tie it to Webb, which is the telescope that just launched. Here's the comparison. The Spitzer primary mirror here is less than a meter. It's 85 centimeters. Hubble's primary mirror is 2.4 meters across. There's a person for scale. This is on the same scale. Webb's mirror is 6.5 meters in diameter. It's a beast, right? It's huge by comparison. So Spitzer is really very much smaller, very, very much smaller than Webb. So now I have a whole series of screen snapshots to talk about all the different orbits that are involved here. And all of these screen snapshots are from a program called Eyes on the Solar System that is from JPL, NASA's Jet Propulsion Laboratory, which is just up the road from me here in Southern California. If you have not played with Eyes on the Solar System yet, you should. It's really cool. So this is Hubble, the Hubble Space Telescope. It is in low Earth orbit. So it's only a couple hundred nautical miles up from the Earth. And there are a lot of satellites in low Earth orbit. It's probably what you think of when you imagine a spacecraft in orbit. That's probably what you think of. And so you can see there's these tracks in the background here. Those are just a few of the spacecraft that are in low Earth orbit. There's a lot of things in low Earth orbit. So I'm going to zoom out a little bit from the Earth. That's Hubble's orbit down there. You can see there's lots of other orbits hanging around in there. Where are the other telescopes? You have to go out pretty far. There's the Chandra X-ray telescope. It has a long elliptical orbit. In fact, it goes a decent fraction, about a third of the way to the moon on every orbit. So if you zoom out further, you might be able to see there are two satellites called Van Allen Probe A and Van Allen Probe B. Those two spacecraft are specifically designed to study something called the Van Allen belt. This is a belt of magnetically charged particles that are trapped in the Earth's magnetic field. And those spacecraft, those two Van Allen probes, are designed to sit in that Van Allen belt. The difficulty is that those Van Allen belts are really hard on spacecraft, and Chandra goes through them almost every orbit. And Chandra is designed to focus X-rays. And when you know how to focus X-rays, you know how to focus charged particles too. So every time Chandra goes through those Van Allen belts, because it's focusing, the mirrors on Chandra are not the same mirrors that you imagine, like when you check your appearance before you leave for the day. Chandra's mirrors are not like that. Chandra's mirrors are cylindrical because they have to be able to focus X-rays. And so the X-ray photons skim off the surface of these cylindrical mirrors, just like particles do. So every time Chandra goes through those Van Allen belts, they're focusing particles on the detector, which is bad news for the detectors. So Chandra has to shut itself off every time it goes through the Van Allen belts, which is hazardous. If you don't shut it down, it's bad for the detectors. So you have to keep zooming out. We haven't found Spitzer yet. Now, this is kind of sort of now. There's the sun in the middle. Earth is at the top. You might have heard of a spacecraft called Kepler, which is no longer functioning, but looked for planets. Spitzer, it's all the way out here. There's Mercury, there's Venus. So right after launch, Earth was there. Spitzer got kicked out from Earth. So it is in an Earth trailing orbit. It orbits the sun just like Earth does. So 5 years after launch in 2010, that was the end of the nominal mission. And it's when Spitzer actually ran out of cryogen, right? It ran out of the liquid helium that we carried on board that helped to keep the spacecraft cool. But it turned out that the thermodynamics of Spitzer were pretty spectacular, and it could keep itself cool, pretty cool, just by passively cooling. And so that the two shortest wavelengths it could still continue to observe. And so it's just continuing to trail away from Earth in Earth's orbit. So the main takeaway points here is that Hubble orbits Earth very close to Earth. Chandra orbits Earth, but in a long elliptical orbit. Spitzer does not orbit the Earth. Spitzer orbits the sun, and Spitzer is trailing slowly away from us. Spitzer's orbit is really good because we don't need to worry about avoiding the Earth and the moon. The Earth and the moon turn out to be really bright, and Hubble spends half of each orbit simply not looking at the Earth and the moon because it's so freaking bright. Okay, it goes around every 90 minutes, and half of each orbit, it simply can't. It has to close its eyes. It can't look at the Earth and the moon. And there's no Earth radiation belts where Spitzer is, so there's no damage to the detectors or the electronics, so that's also good. And because it's trailing away from the Earth, it's a really good thermal environment and it allows Spitzer to just passively cool. And cool is really important. So because we're trying to observe in the infrared, that's really important for the spacecraft to be cool. So it had a 5.5-year nominal life. it operated below 12 Kelvin for those 5.5 years. And then after we ran out of cryogen, we could just passively cool. We could operate at about 28 Kelvin starting in July 2009. And there was only 2 wavelengths left, but they worked just like they did beforehand. And then we officially turned off in January 2020, which means that we have 16 years of data to mine. So connecting all the dots here, this Earth trailing orbit, plus the fact that we needed to be passively cool, plus the fact that we have no moving parts, means that the spacecraft has to turn itself to talk to Earth. But the antenna was designed to communicate when it was relatively close to us, which means there's a natural end to Spitzer's mission. So here, this graphic is trying to explain that. Whoops, come back. So here's the Earth. This is a different graphic. The sun is here, the Earth is here. So when Spitzer was launched, it's going to trail away from us. This is the antenna for Spitzer. And you see it has to turn to talk to Earth, and the spacecraft's solar panels are still facing the sun. This is about when we ran out of cryogen. We're going to continue to trail away from the Earth. Now, in order to communicate with Earth, look, the spacecraft's solar panels are no longer quite so squarely on, pointed at the sun. So this is bad news for charging the batteries and for keeping the spacecraft cool. If you've ever had like your cell phone, when you're relying on your cell phone for directions and you're running out of battery, like, please hold on, I just need to get where I'm going. You finally get where you're going and you have a place to plug it in. You may have noticed that when you plug in your cell phone, especially when the battery is really low, you can feel your cell phone heat up as it's charging its batteries. That's what happens here too. So we would point the spacecraft's antenna to Earth, talk to Earth, but spend the batteries down while we were talking to Earth. And then when it was done communicating with Earth, spending down its batteries, we'd slew away and then just wait for it to charge its batteries and then wait to cool down after charging the batteries before we could resume science. This movie is another visualization of that. Here's the sun, here's Earth. This is right after launch, so we can turn to talk to Earth, no problem, and keep the spacecraft's solar panels facing the sun. But later and later and later, now we're reaching the point where the sun is pointing at the bottom of the spacecraft and no longer square on the solar panels. So that is a natural end to the Spitzer's mission. So where is the new telescope? Webb, just earlier this week, is another totally different orbit. Webb is going to something called the L2 point, the Lagrange 2 point. So it is, again, also far away from the Earth-Moon system, but it is not, and so it is also orbiting the sun, but it is not trailing away from Earth. It is at a constant distance from Earth. So the communications are not nearly as challenging. I have a movie of this one too. So here it's the view is going to change. It's orbiting this L2 point and it's got the Earth and Moon there too. So the camera's going to move down here. So it's doing sort of a loop-de-loo around the L2 point, keeping its solar panels facing the sun. And its communications are relatively easy because it's staying the same distance from the Earth and the Moon. But it also needs to stay cool, of course, because it is doing some infrared observing as well. Come on. All right, so what did we study with Spitzer? Sort of the snarky thing is the old, the cold, and the dirty, right? So we're studying very old things at the distant galaxies, the beginning of the universe. We're studying very cold things and very dusty or dirty things. So stuff in the solar system. I suspect you know that Saturn has rings, but I bet you didn't know it has a really big ring. Spitzer discovered a very big, very fluffy, very diaphanous outer ring of Saturn. This ring is visible only in the infrared. If we could see it, even if we were standing in it, we might not know it was there, but it is 2 full moons across. So this is an artist's conception. Saturn is down in the very center there. This is an enormous ring and it's inclined with respect to the other rings. It's tilted 27 degrees off from the rest of the rings. And it turns out that Phoebe orbits within it. And Iapetus is another moon and it's dark on one side. So sort of like when you go on a road trip, you end up with the bugs on your front windshield, but not your back windshield. That's exactly what's going on. So here's another view. There's Saturn down in the middle, Titan, another famous moon of Saturn, is right close to it. Iapetus is here, and Phoebe is almost certainly the source of the dust. And so Iapetus is dark on one side, and for years, no one knew exactly why. Iapetus is going face first through the dust ring generated by Phoebe. So it's dark on one side, and that's why. And Spitzer found the ring. Stuff in our galaxy. So as some of you, as Kathy alluded to when she introduced me, I have a lot of family on this call. So let me explain a little bit about why that's important. So Spitzer has revolutionized our understanding of our own galaxy. So how do we study our own galaxy when we're in it? I've been giving public talks like this for, I don't know, at this point, 30 years. And I have struggled for years explaining how do you study our own galaxy when you're in it, when you can't view it from another angle. And because we do have lots of family in West Michigan, especially when my kid was small, my kid would get really excited about getting on a plane. I mean, really excited. I mean, when he was a toddler, I thought for sure he was going to end up being a pilot. Now he wants to be a marine biologist, but that's fine. When he was a little kid, I thought for sure he was going to be a pilot. He gets so excited about getting on a plane to go visit the family in West Michigan. And you know, we're getting on the plane at one point when he was a toddler. And of course, we gave him the window seat because why wouldn't he? We got on the plane, we're getting all settled down back in the cattle section, you know, back in steerage, right? And I see him, he's got his face pressed up against the glass. I'm like, what are you doing? I'm trying to see the pilot. That's the analogy. That's how to explain how you study our own galaxy when you're in it. That's it. And I'm like whacking my husband. That's it. That's how to explain it. And Dave's like, what are you talking about? This is what I'm talking about. Okay, so we're in our galaxy. How do you study your own galaxy when you're in it? How do you study your own plane when you're in it? And you can't move, just like we can't move within our galaxy, you can't move within the plane. You're sitting in the plane. You have a limited view of what you can see. If you got your line of sight just right, well, you can see the seats around you, no problem. But if you have your line of sight just right, you can see that there's stuff beyond the seats that are around you. If you're lucky, you have a view out the window and you might be able to see other planes. Whoa, other planes have tails. Do we have a tail? I don't know. We can't see our tail. We must have a tail because other planes have tails. Oh, you look out the window, we have wings. We definitely have wings. And other planes have wings. That's good. We have wings. All right. Do we have a pilot? Other planes have pilots. We cannot see our pilot. There is no way we can see our pilot. There's too much stuff in the way. There's other seats, there's other people, there's that dorky curtain, and there's a door in the way. How are we going to see our pilot? No amount of squishing your face against the glass is going to solve the fact that we can't see our pilot. But if you pick the wavelength of light just right, you can see through all that stuff. You can see through the dust between us and the galactic center. You can see the pilot, you can see the galactic center, you can see the structure of our galaxy. And that's how Spitzer does it. You can use the infrared light to see the structure of our galaxy, even though there's no way that we can ever get up above or below our galaxy and see the structure of our galaxy, but you can still uncover the structure of our galaxy using infrared light. And that's what Spitzer did. This is an artist's conception explaining the structure of our galaxy based on Spitzer observations. Turns out we knew we lived in a spiral galaxy, but we didn't know necessarily exactly where those arms were. We live in a barred spiral, it turns out. And so Spitzer helped us understand exactly where those arms were and exactly what the structure was. We're seeing the bar and the arms better than we ever have before, thanks to Spitzer. So this is the data. This is a movie with that data that was used to spell this out. So we're scrolling through the galaxy, and you see in the bottom here, this cone shows you what we're looking at. And this is the galactic center here as we're moving through. This picture is the largest astronomical image ever taken. If it's printed out at full resolution, it would circle the Rose Bowl. Okay, it is an enormous, enormous image. But it has opened the doors to our understanding of what our galaxy structure really is. Because it's using the infrared, because we can see through the dust, we can understand better the structure of our galaxy. Here's another view of that long image. This is the galactic center, and it runs off the edge here. It picks up here, runs off the edge here, picks up here. You see, you get the idea. It's a long stripe, right?
How did we identify the arms? How many arms we have based on this?
So you look at the brightness of the stars, and once you know a little bit about the kind of stars they are, you can look at the brightness, and you can, if you have two stars that are the same type, they're the same type, but they're different brightnesses, you can figure out how far away they are. Right?
Okay.
And then you can understand then what the structure is. Okay, so another big revolution that infrared astronomy has brought us is an understanding of how basically it's how planets form, basically. So in my experience, in the popular science view, right? In the popular science view, astronomy, scientific discovery sounds like eureka, like jumping out of the bathtub, running down the street. Eureka, I've discovered something. In my experience, scientific discovery does not sound like that. In my experience, scientific discovery sounds more like, oh, that's weird, right? So the entire way that astronomers measure brightness of things is entirely based on empirically measuring the brightness of a relatively small set of stars. And it all comes back to Vega, a star called Vega, which never mind, it's a long explanation, but it basically all comes back to Vega. So whenever you commission a new telescope or a new instrument, most people will try to observe Vega as well as like a dozen other stars, but everyone comes back to observing Vega because that's the basis of the measurement system. So when the very first all-sky survey in the infrared was started with a satellite called IRAS, which was launched almost, 29 years ago, this week, the very first thing they did, well, they were doing an all-sky survey, but the very first thing that they did was start to pull out the measurements of Vega and a handful of other stars whose brightnesses they thought they knew. And Vega, as well as like a dozen other stars, were too bright. Like, that's weird. So like 20 of the stars were like the brightness they expected, but some of them were way too bright. It doesn't make any sense. And they tried to figure out what was wrong. They tried and they tried and they tried. Didn't make any sense. Okay, we're gonna go with the 20 we understand. We're gonna calibrate the spacecraft. We're gonna move forward with what we do understand. But then we're gonna circle back and try to figure out why these dozen stars are so bright. It doesn't make any sense. And so they tried and tried and tried to figure out what was wrong with what they were doing. Why were these dozen stars so bright? Well, it turns out the reason they were bright is because they have dust around them. And that was the opening salvo to answering the question of, are we alone? Are there other planets? Are there other life forms out there? This was the beginning of our understanding that definitely there are other planets out there. That was the beginning of understanding that, there are definitely other planets around other stars. So this was about what I'm going to show you here is an artist's conception, but this is almost certainly what Vega really does look like. Vega is a very, very blue star, and it has a big honking dusty ring around it. And that's why it was brighter than expected in the infrared, because that dust around Vega intercepts the light from Vega, heats up, just like your steering wheel in your car, and re-radiates in the infrared. And that's why Vega was so bright in the infrared. And so that dust around it is almost certainly a signature of planet formation around Vega and other stars like it. So this is the story of star formation. This cartoon is the story of star formation. So you start with a big cloud of gas and dust. It starts out collapsing in on itself due to gravity, and just because of the way that gravity works, it doesn't fall straight in. It falls onto a disk first, like a record or a compact disk, and falls onto the central star. And for reasons nobody understands very well, but almost certainly involves magnetic fields, jets form above and below the disk. Eventually that cocoon of matter disperses either because it falls on the disks or gets blown away by the outflows. And then you still have high accretion rates and you still have the jets. Eventually that disk thins out and forms planets. Eventually you have a genuine bona fide hydrogen burning mortgage paying adult star with a planetary system around it. That's how you get a planetary system with all the planets in the same plane going in the same direction. That's how you form a planetary system like ours. And Spitzer has helped flesh out this story and helped populate this story in ways, that far exceeding expectations. So here are pictures of actual Spitzer data that flesh out that story. So this is one of those, the earliest stages, one of those dark clouds. There were a bunch of things that were known prior to Spitzer as starless cores because they were the earliest stages, although surprise, this one has a baby star inside of it, and Spitzer discovered that baby star within it. This is another dark cloud in the visible. And when you look in the infrared, it's got some big honking jets coming off of it. There's an edge on disk and big honking jets coming off of it. This is one of my favorite star forming regions. Everything green here is a jet. So it's a huge number of baby stars. All of the green things are jets. This is a Hubble Space Telescope image. It's the most famous Hubble Space Telescope image. It's called the Pillars of Creation. M16 is the Eagle Nebula. These are the talons in the eagle. And what's happening here is you have a big, bright collection of high mass stars putting out so much energy, they're pushing around the gas and dust. And that's why you get these pillars. But this is a relatively tiny chunk of sky. There's that footprint, that funny footprint from Hubble there. Spitzer can cover huge chunks of sky really efficiently. So that's optical. In the Spitzer, this is infrared. So here there's that long, that red is actually 70 microns light. So very long wavelength light. Turns out that Spitzer discovered this is the remnants of a supernova explosion. So the supernova is what's crumpling the towers.
Did you say the image on the right that's visible?
The
Like
funny
the smaller
footprint,
one?
that chevron, the chevron is in the optical. Yeah.
So that's what your eye would see, like if you look through the telescope?
So it's complicated. Your eye only integrates for a fraction of a second, and the space telescope can integrate for much longer. So if you actually put your eyeball to the telescope, you wouldn't see that because your eye can't integrate that long.
But that's what it looks like. It's just we can't see it. So like,
yeah,
telescope-
this is light that you can see. Yes.
got it.
But it's, yeah, Hubble doesn't have an eyepiece. So
Yeah, that's what, yeah.
Yeah, but it is optical wavelengths, right? And
Yeah.
it turns out that this is also line emission, and your eye doesn't have a filter. So your eye integrates over much, the large chunk of the optical bandpass. But yeah, but the big image is in the infrared. So this is some of my favorite data because it's my data. So on the left is optical, on the right is infrared. And this is called the North American Nebula and the Pelican Nebula. You can see the North America, right? Because there's Maine and the Eastern Seaboard, and there's Florida, the Gulf of Mexico, and there's the Mexican Riviera. You can kind of see the North America. The pelican is harder to see. That's the back of the pelican's neck. That's the pelican's beak, the pelican's belly. You see it? That's infrared. It looks totally different. This is the Gulf of Mexico. That's the Gulf of Mexico cluster, which I got to name. That's here. That I called the pelican's hat because, it is. That's the back of the pelican's neck. That's the back of the pelican's neck. This is the Mexican Riviera. So is that. It looks totally different in the infrared. You get this huge star forming region. So literally thousands of baby stars. Yes, I got to name them. No, they don't have cool names. They just have numbers for names. So this is just zooming in on that Gulf of Mexico. So all the green things are jets. There's literally thousands of baby stars forming in there. I haven't shown any spectroscopy yet, but I do want to show at least one. So spectroscopy, basically like a prism, it breaks up the light into constituent parts. There's brightness as a function of wavelength. This is a spectrum of a big comet called Comet Hale-Bopp that visited us in our solar system several years ago. This is a spectrum of the outer disk of a star forming or a planet forming disk. And it's all of those brighter green features are olivine, like green sand beaches in Hawaii. The important part is all those bumps and wiggles match these bumps and wiggles. So the stuff that Comet Hale-Bopp is made out of is the same stuff that this outer disk in this other planet, on this other disk is made out of. So Spitzer has increased the number of young stars known by several factors of 10, many orders of magnitude. And there's planet forming disks everywhere. So there's no wonder that so many stars have planets. I am running out of time. So I'm going to skip some of these exoplanet stuff. I think I'll just do one of the exoplanet things. Spitzer doesn't discover planets, but it helps us characterize planets. And there's many different ways to work with exoplanets. I'm going to just talk about the transit photometry, which is one of the ones that is most popular, that people is probably the easiest to understand. In those cases, you have a planet going around a star, and usually it's explained where the planet goes behind the star and blocks a little bit of light, so you see a little bit of a dip. But in the infrared, because the planet is bright, when the planet goes behind the star, not in front of, but behind the star, you get a dip of light because the planet is bright in the infrared. So you're seeing, that means that some of the infrared photons you're getting are coming from the planet itself, which is really cool. So this is the first discovery images of exactly that. Tiny little dips. This is brightness as a function of time. These are tiny, tiny, tiny little dips from these two planets around two different stars. And they're there. They're real dips from this planet itself. And the planet system that we're most famous for is called TRAPPIST-1. This is an artist's conception. You've got this M star, which is a much less massive than the sun. It's a very, very red star. And it's got 1, 2, 3, 4, 5, 6, 7 planets around it, very, very, very close to their parent star. So close that there's steam around the closer stars, liquid water halfway out, and ice further out. I'm going to skip some of that. This is the, I'm going to skip some of that just in the interest of time. The bottom line is that there's a whole bunch of stars. It's actually a whole bunch of planets around this star. It's actually much closer to Jupiter and its major moons in both scale of the central object and the scale of the orbits than it is our solar system. The TRAPPIST-1 system can fit well within Mercury's orbit. It's much more similar to Jupiter and its Galilean satellites than it is our solar system. But this is what that light curve, that brightness as a function of time looks like. You've got the brightness, the total brightness of the star plus planets, and then you get these little dips from the planets occulting the star. So you get these tiny little dips, and you can identify which one of these dips goes with which one of these planets. And this is, there's a whole series of these Exoplanet Travel Bureau posters. If you can get them online, this is likely what you would really see if you were sitting on TRAPPIST-1e, because these planets are so close together, you would probably see them all. They would dominate what you saw in the sky if you were standing on TRAPPIST-1e. They are so close together. I'm going to skip these because that's okay. The final punchline is that all of these data are yours too, because you pay taxes and all of these data are yours too. So this is one way to get access to them. There's a website called Cool Cosmos, and there's lots of really cool pictures of everyday things in the infrared. There's lots of infrared universe pictures and a history of infrared missions. There's also lots of other resources as well. We talked a little bit about the use of infrared in firefighting. I live in the foothills, north of LA. You may have heard that we have fires. We have a lot of fires. So all of the fire, the foothill communities here, all of them have helicopters with infrared cameras on them because fires in the hills are a really big deal. And so they're always looking for fires in the hills with infrared cameras. And they also, it turns out, look for fugitives. And there was one, we had a really bad heat wave several years ago where it was like 110 for several days in a row. And they were tracking a fugitive up in the hills. They found him because he was, wait for it, cooler than the rocks he was running through. But yes, so all of these, the emergency crews have infrared cameras on helicopters. So there's lots of stuff on firefighting and search and rescue, use of infrared. They also use infrared for just general environmental monitoring. They use infrared in art restoration and in archaeology, also in veterinary medicine. So there's lots of applications of infrared. I don't know how it might apply to supply chain. I did try and think about it, but maybe you guys can think of something. And then I'll leave this last slide up for a little bit. This is where to go to find some of the things we talked about. You might be interested in the Spitzer website. There's a whole series of IR relevant or irrelevant astronomy videos where we've involved some of the Hollywood stars talking about astronomy stars and concepts in videos. There's the Universe Unplugged videos, which are also fun, also involve stars. And we also have Ask an Astronomer videos, sessions on Facebook once a month. There's a website specifically for the end of Spitzer. There's the Cool Cosmos website that I just was mentioning. If you have a virtual reality headset, you can get Exoplanet Excursions, which talks specifically about the TRAPPIST-1 system. There's the Exoplanet Travel Bureau that has a whole series of posters, but they also have an interactive website. I mentioned the eyes on the solar system. There's also an app called NASA Selfies. So if you go to the App Store and Google that and look for that, you can put yourself in a spacesuit in front of a whole bunch of Spitzer images. If you are a fan of the Dead Tree version of looking at things, there's a book called More Things in the Heavens by Werner and Eisenhart that came out in 2019 that talks about all the fantastic things that Spitzer discovered. If you're a high school teacher and you would like to do astronomy research with me, Google NITARP and apply to come work with us. And then if you want to know when we will get results from Webb, they just reached their orbit earlier this week. They are still finishing cooling off. They need to finish adjusting their mirrors and commission the instruments. So in about 5 months, likely we'll start to see some science results. We still need to finish that process. And there's lots of websites on Webb, but that's just one of them. We can figure out exactly what they're doing, exactly where they are in that commissioning process. So thanks for your attention. Hopefully I've only run 30 seconds over my assigned time. So I'll take any more questions that you guys have.
This is really cool. Thanks for the presentation. Now, when you look at James Webb, which is enormously huge compared to
Yes,
Spitzer,
it is huge.
what kind of discoveries are you expecting from it?
So the Webb is going to study lots of, well, let me put this back up in case people are still writing down links or taking screen snapshots to get the links. They're going to be studying things that are, in comparison to Spitzer, faint, right? Because they have a much bigger mirror. So they're going to be able to study things that are at the very beginning of the universe, very, very faint galaxies at the beginning of the universe. They're going to be able to study exoplanets. So exoplanets are very difficult to study because in general, they're very faint compared to their host star. So it's kind of like trying to study a moth circling one of those spotlights that you might think of when you think of Hollywood premieres, the big spotlights, a moth circling spotlight. So in order to try to do that, Webb has lots of tricks that they're planning on doing so that they can make that work. But they're going to be studying exoplanets. They're going to specifically try to look at the constituents of the atmospheres of exoplanets. And they're going to specifically trying to be studying the very earliest stages of star formation, because they're going to be able to do that because they have near infrared and they also have lots of spectroscopic capabilities. And because they are so big, they're going to be able to look at very, very faint things. So that's some of the things that they're going to be doing. I'm sure they're going to be doing a lot of different things, but a lot of the things that they're going to be focusing on are the exoplanets and the edge of the universe, very earliest galaxy stuff. Those are the things that they're really pushing.
Okay, very good. Thanks.
More questions, or have I put you all to sleep?
Oh, no. So this might not be something that's pertains to telescopes necessarily, but I recently was heard that they had started doing underground mapping of lithium mines and stuff in the Salton Sea. And I think it was that they were using either infrared radiation or it might have just been electromagnetic radiation. Is there ways that we can use, that people use IR, to find not just what's up in the sky, but what's below our feet?
That's probably radio.
Okay, radio.
Yeah, probably radio. Yeah, because so infrared will go through dust, but does not easily go through brick. It doesn't easily go through rock, right? You need radio, right? So radar to go through things like that. So it's if they're looking for mines, they're probably using radar.
Yeah, I think that they were using it to find underground reservoirs of where they might find lithium for batteries.
Yeah, probably radar. I don't know very much about that, but
that's okay. I was just a question. But thank you. This was super interesting.
Good. I'm glad.
Well,
thanks again so much.
You're welcome.
It's great. Yeah, it's good. Thank you.
So if we don't have any more questions, is there anything more, Louisa, you'd like to tell us for 5 minutes, or what would we like to do?
Well, I mean, I don't know. Are there really no more questions, or are people just shy?
Say this is I have a question. Does anything of these cameras or the Spitzer or anything, the study of the global warming from the outside, how does it work with the infrareds and stuff like that?
So because we're studying things, we look out from the solar system.
Okay.
If we looked at the Earth and the moon, we would blind ourselves. If you've ever do you remember how when someone takes your picture, if you look at the flash, right, afterwards you're kind of like, oh man, you got the bright spot.
Mhm.
Yeah, that only permanent damage to the detectors, right?
Oh,
So we can't look at the sun, we can't look at the Earth, we can't look at Venus even. So we try not to look at the sun or the Earth or the moon. We can't, it's too bright. And so there are other people at NASA, right? Because NASA is much more than crewed missions. It's much more than just spacecraft that look out. There's a huge section of NASA that are Earth studying. And so, yeah, there's a huge section of NASA that studies Earth. And so, yes, there are definitely people that study the Earth using infrared. There's definitely people that study weather using infrared and global warming using infrared. And there's you can actually get the weather satellite images every day, I think it's every 30 minutes. There are spacecraft that take images in optical and infrared. So when you get a weather forecast at night, some of that is radar and some of that is infrared imaging, because an optical image at night isn't going to give you any clouds. So the weather loops at night will be a combination of radar and infrared light. So there are definitely infrared images of the Earth, just not anything that I do.
yeah, that's good.
I have one question.
Yeah.
So with Webb being more between the visible and the IR, are there any plans for the future for a more specific IR or a little bit further out wavelength telescope?
Definitely. So the funding lines, I used that phrase earlier. When you work for the government, you have to keep track of exactly how these different things are funded. And NASA funds short, small, cheap missions, medium-sized missions, large missions, and flagship missions. And there are lots of short, small missions that are going all the time. There's actually a congressional mandate, a specific line item in the budget that says we must know how many big rocks might hit us. Swear to God, it doesn't use that language, but it says we must know how many big rocks are out there. So there's actually, and because the big rocks are rocks, they glow in the infrared really well. So one of the next missions that's coming up is doing an infrared survey specifically to look for the big rocks. And oh, by the way, we're going to do astronomy with it, not just look for the rocks. So that's one of the missions that's already in the pipeline to happen, but it's one of the smaller missions. There are much smaller missions. You may have heard of CubeSats. They're literally like Coke can sized. And so people are working on how to send like groups of these little CubeSats out to do interesting astronomy, including in the infrared. I have a friend who's working specifically on how to make a small group of them that would observe in the ultraviolet, optical, and infrared together. And then there's medium-sized missions that are much more focused. There's ones that are, there's one called TESS that's specifically looking for planets in the optical, but then there's also the flagship missions. And so there are 4 that are currently planned right now, 2 of which have substantial infrared capabilities. And so they're all being studied right now. There's different NASA phases. And so they're all currently being planned. There's large groups of people that are planning specifically what kind of technology they're going to need, what kind of technology needs to be developed, what kind of technology do we have, how much money, what kind of development costs are going to be needed, what kind of launch vehicle they can use, and importantly, how much data. You think of, it seems like it would be trivial just to get the data back. It turns out space plumbing is not cheap. Simply getting the data back is substantial. And so you have to worry about how much data are going to come back, how much data processing needs to be done on the spacecraft versus how much bandwidth do you need to actually talk to Earth and get the data back. So all of that planning is happening. And yes, the flagship missions are being planned, and those flagship missions take decades to happen. So they're already moving. There's 4 big ones that are in the pipeline, and will, NASA will down select eventually, because all of the different wavelengths are competing. Just like one of the reasons the great observatories were so successful is they did span the whole range of wavelengths. And so the new flagship missions that are planned deliberately span multiple wavelengths, but NASA will not probably be picking all of them. And so they eventually will down select or defer some of them later, select some to go sooner. So we'll see what happens with that process.
Are there any private missions on these things, or?
Not that I know of. SpaceX and Blue Origin tend to want to send people up because they want tourists to pay, right? That's why they want to, right? So they're interested in the crewed missions. Although having said that, I mean, at least when I watch like a SpaceX launch versus a NASA, so when you watch like a NASA launch of any sort, you look at the mission control, and there are people that look like you, there are people that look like me, there are women in hijab, there are people of a variety of ethnicities, there are people, a wide variety of genders, there are people that look like the American people in the NASA control room. When you look at a SpaceX launch, the first thing I think of is, where are the women? That's only the first problem I have with the SpaceX launch. So yeah, those private launches, there are issues.
I see.
Yeah, there are issues, and I don't see them trying to do science.
Yeah,
They're trying to launch.
Benefit.
They have a different goal in mind.
Correct.
Yeah.
Well, Louisa, this was really fascinating. Thank you so much for presenting to us.
You're very welcome.
We learned a lot, and we
Good.
really enjoyed it. Thank
Good.
you.
I'm glad I could help.
Yes.
Right. Excellent. Thank
Thank
you.
you so much, Louisa. It's great
You're
to hear it.
welcome.
Thank you. Yep.
Great. All right. I will talk
Thank
to you
you.
guys soon. All right.
Right.
Bye.
Yep. Bye-bye.
Bye.
Bye.
Kathy, I didn't get a chance to, let me stop the recording here.
Oh, yeah, whatever. Yes. I see my mom's on, Luke's on, Laura's on, Betty Hoekstra's